The next topic I want to discuss is freefall. Freefall means moving under the influence of gravity alone. So, influence of gravity alone. Well, what I really mean is the only force acting on the object is gravity. Now, we haven't officially defined what a force is, and we won't until Chapter 4. But suffice to say that a force is a push or a pull in a certain direction. I think most folks coming into this class are pretty comfortable with that definition of force. So, what I mean here then is that there's nothing pushing or pulling on the object except gravity alone. And that means that it's in free fall. And we'll talk about why we care about that in just a second, but let's first make sure we know what I mean by free fall. How about this? Is this object in free fall? Well, the answer is no. And why not? Because is gravity pulling on it? Yes, absolutely. Gravity is pulling down on this ball. However, is there another force acting on it besides gravity? And the answer is yes. My hand is pushing on it. So this is not an object in free fall. I doubt if that surprised anybody. How about this? Now I'm going to drop the ball. Okay, was that free fall? Well, technically, there's a little bit of air resistance. But for the sake of this discussion, we're going to ignore air resistance. There's definitely air in my basement because I'm breathing and talking. But we are going to ignore air resistance for the sake of this discussion for the next little while. And so, under those conditions, if I let go of this ball and I let it fall, what forces are acting on it as it falls? Well, just gravity, right? If we ignore air resistance, then, my hand let go, so my hand's not putting a force on it anymore. And indeed, it is just gravity. So is this free fall? You bet it is free fall. How about this? Now the ball goes up and down. Is that free fall? Well, are there other forces acting on the ball besides gravity? Well, on the way down, certainly not. That's just gravity. Again, we're ignoring air resistance. There's this magic moment at the top when it's actually stopped, right? Before it starts to fall back down. And at that moment, there's no air resistance because it's not moving. And at that moment, there literally is only gravity. So I guess that's free fall too, right? It must be because there's only gravity acting on it. How about on the way up? Is the ball in free fall while it's on the way up? Again, ignoring air resistance. Well, the answer is yes, it is in free fall because the only force acting on it is gravity. Now, a lot of folks, when I say that at this point in the semester, they say, well, yeah, but didn't your hand make it go up? I mean, you had to push on it with your hand to make the ball go into the air. And that's absolutely true. But how long did the force from my hand last? The force from my hand lasted only while it was in my hand. You know what? I'm not a Jedi. So I cannot exert a force on this ball when it's not in my hand, right? If it's just sitting right here, can I exert a force on it without touching it? Let's see. No, I cannot. I am not a Jedi. I cannot exert a force on this ball unless I'm touching it. Okay, so is that different when I throw the ball? No, it's not. It's not. The only way I can exert a force on the ball is if I'm touching it. Right? Another way to think about that is, could I make the ball move side to side after it leaves my hand without touching it? No, of course not. So there's no force that persists from my hand after it leaves my hand. So what is free fall here? Well, free fall on the way up, free fall on the way down, free fall at the very top. What if I toss it over here? Is this still free fall? And indeed it is. That is still free fall because we're ignoring air resistance, and an object moving under the influence of gravity alone is in free fall. Now, Aristotle thought, Aristotle thought a rock falls because a rock is made of earth, and a rock wants to be with its its essential nature is of earth, and it wants to be with its stuff. So it falls in. And smoke rises because it's an essential nature as it is of the air, and it wants to be with its stuff. No, that's an all right idea. But it doesn't really work that well if we're trying to, build a helicopter, right? So turns out this idea persisted well into the Middle Ages. In fact, until Galileo. Galileo came along in the 1600s, and he said, well, maybe we can have a better idea here. So Aristotle thought, hey, if I've got a really heavy rock and a really light rock, then the heavy rock should fall faster. In fact, if the heavy rock is 10 times as massive as the light rock, then I expect the heavy rock to fall 10 times faster. And so Aristotle was a Greek, and he proposed this idea, and everyone said, hey, that's a great idea, Aristotle, let's go have some wine. Nice work. And that was the end of it, right? It's kind of crazy to think that it wasn't until the 1600s that somebody came up with an idea for an experiment to test that. I bet you guys could come up with an idea for an experiment to test that. You could just drop a big rock and a little rock and see which one hit the ground first. Guess what you'd find out? You'd find out that they fall at the same rate. In fact, Galileo was the first person to do this, right? And at least record it and write down his observations. And he actually dropped a large piece of lead and a small piece of lead off of the Leaning Tower of Pisa. They fell at the same rate. They hit the ground at the same time, and people were stunned. Supposedly, people didn't really believe that they had actually witnessed that. They thought it was some sort of trickery that he had contrived. So this is part of why we call Galileo the first modern scientist, because he put an emphasis on experimentation. Right? He said, if I have not observed it, then why should I believe it? And it's kind of crazy because, the scientific method and the scientific mindset has really, it's been so successful that it's taken over pretty much every culture in the world. And the idea that you would just propose that a big rock falls faster than a small rock and nobody would ever think to do an experiment to test that. As a modern human, that seems a little bit ridiculous. But really, it wasn't until Galileo and others came along that this emphasis on experimentation and observation came. Mostly prior to Newton and Galileo in the 1600s, 1700s, there was this belief that you could reach the correct conclusion with just pure thinking, with just pure logic. In that somehow doing experiments sort of tarnished that pure logic. So anyway, along comes Galileo. He tries it out, and it works. And nowadays we can do even better than that. Nowadays we can do even better than just dropping a large lead ball and a small lead ball and seeing when they hit the ground. Now it turns out air resistance is a bit of a factor in that situation. And had he chosen a higher building, a taller building, he may not have gotten quite such satisfactory results. But you know what? We live in the 2000s, not the 1600s, and we can do some pretty good experiments these days. Let's check something out here real quick. So here what we're going to see. We are going to see David Scott, who is an astronaut on Apollo 15, and we are going to see him dropping a feather and a hammer on the moon.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon, and I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
Okay, and now let's check out a video done in a very large vacuum chamber at NASA. This is the largest vacuum chamber in the world. Okay, so first here we're going to see the feathers and the bowling ball fall with air present. And I don't think anyone's going to be super surprised at what we see here.
Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So, in order to see the true nature of gravity, we have to remove the air.
And so now we're going to see the feathers and the bowling ball fall with no air in the room.
Cameras on, 2, 1, release.
Look at that.
They came down exactly the same. Wow.
Look.
That's right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing.
Look at that. That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down. Gravity.
Okay, so again, this is an idea first presented by Galileo in the 1600s and pretty easily demonstrated here in the 2000s. So, to put some numbers on all this, acceleration is a vector. And what is the acceleration of gravity? It is 9.8 meters per second squared vertically downward. That is the acceleration of any object if I drop it near the surface of the Earth, neglecting air resistance. Now we use some notation here. G is the magnitude of the acceleration, and so it's positive. So we often represent G as 9.8 meters per second squared. So G is 9.8 meters per second squared. G is always positive because G represents the magnitude of the acceleration of gravity. We know that acceleration is a vector, and so it should include a direction. That direction is down. Typically, we call down the negative direction. And so we should write that the free fall acceleration of gravity is negative g. Again, g being a positive number, the negative sign goes out in front. G is 9.8 meters per second squared near the surface of the Earth. Other planets have different values of g. The value of g on the moon is about 1.6 meters per second squared. Gravity on the surface of Jupiter, if you could find the surface of Jupiter, it's a gas planet, so where the surface would be, I suppose, if it had a solid surface, that's about 2.5 times our g. So it's something like 25 meters per second squared. Okay, so g could be different on different planets, and also g goes down as you get farther from the center of the Earth. So again, g is 9.8 meters per second squared near the surface of the Earth. Other planets can have other values of g. Now, the nice thing about these freefall problems is they tend to become one-dimensional motion problems. And so we can just use the big five like we did in the previous lecture, but now we know acceleration in the y direction is negative g. Let's try a quick example. Here we have an arrow launched up vertically. It moves straight up to a maximum height and then falls to the ground. The trajectory of the arrow is noted. Which choice best represents the arrow's acceleration at the different points? And we are going to ignore air resistance. Go ahead and pause the video and see if you can't figure this out. Okay, so hopefully you made some progress on this. Here we see two dots, A and B on the way up, C at the top, and D on the way down. So the question is, how do we compare these accelerations? Well, we're ignoring air resistance, so what forces are acting on it at the various points? Well, it's just gravity, right? It's just gravity at A, B, C, D, E, all of those places. The only force acting is gravity. And so we say that it must have the same acceleration at all points. What is that acceleration? Negative 9.8 meters per second squared. So what is the acceleration on the way up? Negative 9.8. What is the acceleration at the top, the point marked C in this picture? Negative 9.8 meters per second squared. What is the acceleration at point E in this picture? Negative 9.8 meters per second squared. Always 9.8 meters per second squared, always pointing down, which does kind of make sense. I mean, gravity pulls down, so the acceleration created by gravity should also be down. So we can always express accelerations in units of g. And so here we see that the acceleration in g is simply your acceleration in meters per second squared divided by 9.8 meters per second squared. As a quick example, to ensure the safety of the astronauts, accelerations on board the space shuttle had to be kept below 3 g's. Express this value in meters per second squared. So 3 g's, yeah, it's only context, right, where you can tell the difference between 3g meaning 3 grams or 3 g's meaning an acceleration. It's only context, right? So this clearly can't be grams, right? What would that mean? Accelerations had to be kept below 3 grams? That doesn't make any sense. So it must be 3 g's. And so 3 g's, that means 3 times 9.8 meters per second squared. And so 3 times 9.8 is, of course, 29.4 meters per second squared. All right, let's do a numerical example. Okay, once again, we're just going to read it quickly. We're going to let it kind of wash over us. And then we are going to start transferring stuff onto our piece of paper. So, a pole vaulter is nearly motionless as he clears the bar. It's at 5.75 meters above the ground. He then falls onto a thick pad. The top of the pad is 75 centimeters above the ground. It compresses by 50 centimeters as he comes to rest. What is his acceleration as he comes to rest on the pad? Okay, so I know the problem is something about a pole vaulter. I can't really wrap my brain around too much more of it at this point because I just read it once real quick. So now I'm going to go back and I am going to start transferring information to my... A pole vaulter is nearly motionless as he clears the bar. It's at 5.75 meters above the ground. Okay, so here's the bar. Here's my pole vaulter. It tells me that this distance is 5.75 meters. Okay, so that's that. He then falls onto a thick pad. The top of the pad is 75 centimeters above the ground. Okay, so my pad is here, and so then this distance here is 0.75 meters, which of course means this distance here is 5 meters. Okay, it compresses by 50 centimeters as he comes to rest. Okay, this is getting a little bit complicated, isn't it? That's okay. Let's just draw ourselves a little picture. This is going to get compressed by 50 centimeters, or 0.5 meters. Okay. What is his acceleration as he comes to rest on the pad? Okay, so let's see. Good grief. This seems like we don't maybe have enough information or something, doesn't it, right? So it tells us he's stopped here, and then it wants his acceleration as he comes to rest on the pad. Well, this is a good example of a problem where you can't just answer the question that's asked first in one go. So I picked this problem because it is a two-step problem, which often we're going to see one-dimensional motion problems that are like this, that are two-step problems, where it seems like it's one really hard problem. It's not. Really, it's two easy problems, and that's our number one problem-solving strategy in this class. I promise never to ask you any hard physics problems. I could ask a physics problem that was actually like 3 or 4 easy problems strung together, and it might appear to be hard, right? But if you can break it into these small chunks, then it's not too bad. And so I would say actually that until we can figure out his acceleration here, in order to figure out his acceleration here, we really need to know how fast he's going at the top of the pad. So first, let's find out how fast he's going when he hits the pad. Okay, so we're going to do that first. That means we need to pick what our initial and our final points are. So my initial point then is going to be here, and my final point is going to be right there. Now, final doesn't mean the end of everything. Initial doesn't necessarily mean the beginning of everything. Really, these are just 2 points in the evolution of the system. So, I'm going to make my list of 5 things. Delta x, v initial, v final, delta t in A. Again, for sort of the first phase of this problem, just him falling until he hits the pad. It's a y problem, so I really should replace this with y. Okay, so delta y, do we know that? Well, it's 5 meters, but it's 5 meters in what direction? The downward direction. And so this should be negative 5 meters. The initial, it says he's nearly motionless. Let's go ahead and call that 0 then. V final, ooh, we don't know that. How about A, or delta t? We don't know delta t. And acceleration. Ooh, that is negative g, or negative 9.8 meters per second squared. Okay, so now we've got our list of things. Let's look at our big 5, or excuse me, which thing are we looking for? Well, I said we need to find the velocity when he hits the pad. Isn't that v final? So we're looking for v final, but there's one of these that we're not asked for nor given, and that is delta t. We don't know how long he's in the air, nor do we care how long he's in the air. And so we'll see that equation number 3 has no delta t. So a good clue is, if there's a variable that's not asked for or given in the problem, then we can look for the equation that does not have that variable, and that might be a good place to start. Okay, so here we have our, again, another good thing to always keep in the back of your mind is, once you have 3 of this 5 filled in, you can always find the other 2. Always. Okay, so we've got this. Equation number 3 will work great. It does not have a delta t in it. So we'll write v final equals v initial, v final squared equals v initial plus 2a delta y. Anything that's 0 we should get rid of right away. That's v initial. And so we see here that we can solve for v final. V final equals the square root of 2a delta y. We can plug in our numbers. The square root of 2 times negative 9.8 meters per second squared times delta y, negative 5 meters. And we can run our calculator, and we can just get an answer now. And when we do that, we get 9.9 meters per second. Okay, so we're not quite done yet, but what we have done is we've found the final velocity. What do I mean by the final velocity? The velocity right before he hits the pad, or right before he begins slowing down, right as he's hitting the pad. So there's this sort of magic moment when the pole vaulter has just barely started to touch the pad, but he hasn't slowed down yet. That's the point we're talking about. That is his velocity at that point. Now we're ready to answer to do the problem, to answer the question that's asked, which is, what's his acceleration as he's hitting the pad? And so this I would call is phase 2 of the problem. Let's go ahead and make our list. Now, what is going to be our initial and final point? Remember, initial and final are just 2 points in the evolution of the system. So the fact that we picked initial and final here doesn't mean we're stuck with that, right? In fact, what was my final point is now going to be my initial point. So now my initial point will be there, and my final point will be when he's come to rest and stopped on the pad. Okay, let's go ahead and solve that. Let's make our list of 5 variables. So we have delta y, v initial, v final, delta t, and a. Delta y, again, he's going down. He's compressing the pad 0.5 meters since he's going down. That's negative 0.5 meters. The initial velocity for phase 2 was our final velocity for phase 1. So that is 9.9 meters per second. Now, we actually, I skipped a little something down here. Maybe some of you caught me. Maybe some of you didn't. When I did my square root here, we know that we're always going to get a plus or a minus. Right? Anytime you undo a squared by using a square root, you're going to pick up that plus or minus. So it's either plus or minus. Either plus or minus. Which one should we pick? Well, he's going down. So really, I should have picked my negative here, right? So his final velocity there is negative 9.9 meters per second. And again, just running your calculator won't give you that negative. You just have to pick it out, right? Okay, V final, he comes to rest, so that is 0. Delta T, we don't know, and we're not asked about it. A is what we're looking for. Some of you might be thinking, hey, isn't A negative 9.8 meters per second squared? Didn't we just learn that? Ooh, we did, but only for objects where the only force on them is gravity. Now, in this case, we have the force of the pad acting on him as well, and so he's not in free fall while he is touching the pad. So now we look at that. Which equation should we use? Well, once again, we're not asked for or given delta T. Equation 3 does not have delta T in it. That is our best bet. Okay, so let's go ahead and do this. Equation number 3 looks like this. V final is 0, so that goes away. And now I can solve for the acceleration. And we end up with acceleration equals negative V initial squared all over 2 delta Y. And so this is negative 9.9 meters per second squared divided by 2 times negative 0.5 meters. And when we run our calculator, we get 98 meters per second squared. Okay. Is that a reasonable number? Oh, it's pretty high. That is 10 G's. So it's on the high side of any number I would expect if it's a question about a person. But at the same time, 0.5. So he had the same change in velocity, the same change in speed over half a meter as he did over 5 meters initially in the first phase. So 1/10 the distance, 10 times the acceleration. That seems somewhat reasonable. Yeah, this is a good number. I did answer the question. It asked for acceleration. Okay, I'm feeling pretty good about it. Okay, now you try one. This is a true story. It's been a number of years now. It's probably been about 8 years. My friend Donnie was working on a carpentry crew a few years ago when he fell 5.5 meters off the top of a building onto a concrete slab. This is a true story. He could not walk for a long time, but he is actually working as a carpenter again and can now walk. So it has a happy ending. 2 questions. How fast was he traveling when he hit the ground? And how long was he in the air? So pause the video. Try this out on your own. And I really suggest that you do that. Do it on your own. And if you can't make it all the way through, that's totally fine. But get started. Get as far as you can. If you get stuck, and hit play on the video again until you can get moving again. And I want you to do as much of this as you can on your own. And I've given you some options here. Okay. So I'm going to jump in. What should we do first? Well, we should probably draw ourselves a picture because it helps us to visualize the situation. Now, a lot of people want to skip the picture because they think that it just takes too long, I guess. But man, I mean, the picture is a super important part of it, right? I'm not telling you to draw a picture because like I'm getting kickbacks from the Physics Picture Society of America or something, right? No, I'm telling you to draw a picture because I honestly think that it is the fastest way to get their answer correct the most often, right? And that's really what I want for you. So that's why I'm recommending you draw a picture every single time. I certainly do, and I've been practicing this stuff a lot longer than you have. Here's my building. It says it is 5.5 meters tall.
That's a big building.
It is. Okay, 5.5 meters tall. And he's going to fall off. I'm going to call this my initial point, and this is my final point. Okay. It's not super complicated picture, but it's going to do the job here. Now let's make our list of 5 variables. Delta y, v initial, v final, delta t, and a. All right, let's see what we can fill in here. Delta y, do we know that? Yes, we do. It is 5.5 meters, but we have to be careful because it's down. All right, v initial, what is that? What is v initial? Well, assuming that he's not moving at the top there, then that would be 0, right? V final, that's one of the things we're asked about. Delta T. Oh, that's another one of the things we're asked about. A. I think we can safely ignore air resistance here. So this would be a free fall problem. His acceleration then is negative 9.8 meters per second squared. Okay, so again, we're at that point that you need to start learning to recognize, which is we've got 3 out of the 5 filled out. That means we can always find the other 2. And it really doesn't matter which order we go in. We can either find the final velocity or delta t first. Really and truly does not matter. So let's go ahead and find delta t first. How about?
Oh.
Which equation would you pick to find delta t? Hopefully you've already done it. So let's write it down. Delta y equals the initial delta t plus 1/2 a delta t squared. Again, we should plug in anything that's 0 right away because it makes our algebra easier. That's 0, it's going to go away. And so I can now solve for delta t. And I get delta t equals the square root of 2a of 2 delta y over a. Now, I don't need to worry about my plus and minus on this one, do I? Because, presumably, a delta t is always positive. In my life, it is. Okay. So, delta t is positive. Here we go. We run our numbers. Delta t is the square root of 2 times negative 5.5 divided by negative 9.8 meters per second squared. And now it's time to run your calculator. And I get 1.06 seconds. Okay, now let's figure out how fast he was going when he hit the ground. Now that we've filled in this, right, now we've got delta t figured out, so we could go ahead and fill that in. We've got that, that's 1.06 seconds. And anytime you've got 4 out of the 5, then there's going to be multiple ways that you can go about finding the final. Yep. So this is equation number 2. And we're going to use equation number 1 for this last part. And so this is like this. Again, we're going to plug in anything that's 0 right away. That goes to 0. And we end up with v final equals negative 9.8 meters per second squared times 1.06 seconds. And I end up with V final is 10.4 meters per second. Okay, so that's pretty fast. You know, a lot of times when we're in this assess part of it, we're supposed to look at these answers and see if they're reasonable. I find that most of my students are not super familiar with these metric units, so it's good to have a ballpark unit conversion in your head. If you multiply this number by a little more than 2, then you're going to get a number in miles per hour. So 10 meters per second is slightly over 20 miles an hour. That's pretty fast. You can see how hitting a concrete slab at 20-something miles an hour would cause some damage. Yeah, there it is.